Hello everyone, my name is Balaji Selvakumar and today I'll be presenting our work on the integration of a real-time orientation measurement system for the real-time evaluator or RTE to measure position and orientation of crane-lifted components. This research work was conducted at Oak Ridge National Laboratory and supported by DOE Office of Energy Efficiency and Renewable Energy. The primary goal of our real-time evaluator project is to automate the tracking and installation of prefabricated construction components with higher accuracy using a single watt robotic total station. This system aims to reduce the time and cost associated with installation of prefabricated components in construction, and also the equipment cost by providing a real-time installation feedback through a graphical user interface. Using off-the-shelf construction hardware components, we have developed a system that not only reduces installation time and rework at the job site, but also enhances quality control and minimizes the on-site disruption and wastage. This year, we have made the following changes. We have moved on from Bluetooth communication to Wi-Fi communication for seamless sensor fusion between total station and the and other sensors for extended range and stability. We have also added a real-time orientation measurement unit using Inertial Measurement Unit or IMU. This tracks the orientation and provides orientation updates in real time. Our system is designed to track the installation process and provide real-time installation commands as feedback. It can be used for retrofitting older buildings and newer prefabricated construction projects. The key specification of our system include automation, accuracy with less than 3 millimeter error, and ease of use. This system's ability to provide real-time feedback is crucial for ensuring that the components are installed correctly the first time, thereby reducing the need for costly and time-consuming rework, thereby saving time. Our existing system consists of a single survey-grade robotic laser tracker such as the MS-60 and reusable trackable targets such as 360 prisms from Leica. These prisms are mounted on the panels to be installed and are then tracked using the laser tracker to provide real-time position information for the user or the crane operator. We have also added in real-time orientation measurements such as IMU for providing real-time orientation wirelessly. So the software component is developed in Python and includes modules such as PyGeocom and XIMU for sensor fusion and comparison with the digital twin and provides installation assistance to the GUI. This integration of hardware and software allows for seamless communication, ensuring that the system operates efficiently and accurately. This precise measurement capability is essential for ensuring the components are installed in the correct position, which is critical for the structural integrity and performance of the final construction. For the precise measure function to work, the panels are assumed to be stationary. The total station then cycles between the three prisms to get the orientation at time 0. For each cycle, it takes around 12 seconds per cycle. Once the panel is initialized, the precise position and orientation of the panel is updated in the GUI. After cycling, the total station locks on to the target and tracks the target prism, thereby providing positional feedback in real time. And in order to get the orientation, the total station has to cycle between these three prisms again to get precise orientation. And while it's locked on, it can provide live positional feedback and compared with the digital twin on where the panel is supposed to go with respect to the panel location. When the panel is being tracked, it is not possible for the total station to cycle in between the prisms to get the orientation. So we have added a real-time orientation measurement with an IMU on the loop. This provides approximate orientation updates to the GUI. In order for the IMU to work, it has to be initialized with the panel's reference system for real-time orientation measurement. Once the IMU has been initialized, it can provide approximate panel orientation when it is in motion while moving slowly. The IMU publishes real-time orientation for every 0.2 seconds, thereby providing feedback on roll, pitch, and yaw angles. This this integration ensures that the RTE is able to provide both position and orientation feedback with 6 degrees of freedom at an accuracy of less than 1/8 of an inch. So for the selection of the IMU, we conducted a lab scale tests to compare the IMU's accuracy with 8960 tracker. The 8960 tracker is a highly accurate device to be used as a ground truth. We conducted both static and dynamic testing and evaluated the errors in roll, pitch, and yaw angles of the IMU. During the IMU testing, the movements were executed at higher severity than expected during normal crane lifting operations to ensure robustness of the sensor. The results showed that the IMU is able to provide accurate real-time orientation method measurement with reduced drift over time. The validation process is crucial for ensuring that the system performs reliably under real-world conditions, thereby providing confidence in its accuracy and robustness for integration. So for our lab-scale prototype experimented, we have created a mock-up panels at the scale of 1/3 of the panel retrofit. The panels are mounted on the connection points located on the walls, and they are controlled using a simulation crane. The panels are the prisms are mounted on the panels and along with the IMU, and once the total station is initialized with the panels by cycling between these three prisms, it is able to provide real-time position measurement. At the same time, the IMU is initialized along with the panel, and this provides a real-time orientation measurement. The readings from both these sensors are fused in our software, thereby providing a unified position and orientation on the GUI. This this position and orientation measurement is compared with our digital twin to give the error matrix. This prototype experiment demonstrated that the system is capable to handle real-world scenarios, providing valuable insights into its performance and potential areas of improvement. We compared the performance of the real-time evaluator with and without the IMU, and the results are summarized in this slide. The green color is the goal location of the panel, and red color is the location, live location of the panel that is being tracked by the real-time evaluator. So without the IMU, the total station only locks onto a single prism and tracks the position. But with the IMU integrated, the IMU is able to get the real-time orientation measurement, thereby providing the real-time orientation feedback on the GUI. Again, the green color is the goal location on where the panel is to be placed in the digital twin, and red color is the live location of the panel. In conclusion, we have successfully integrated an IMU for real-time orientation measurement, which avoids the need for cycling between tracking operations and reduces the measurement time from 12 seconds to 0.1 seconds. This system provides a robust solution for accurate installation of prefabricated components in construction. We have also switched from Bluetooth to WLAN communication for optimal sensor fusion between devices. Thank you for providing me this opportunity. Let me know if you have any questions.